the best for the last. So Aditya, Bhaskara is going to talk about residual-based sampling for online low-rank approximation.
All right, yeah, thanks, Anindya, and yeah, thanks for sticking around. Let me start soon so that you guys don't leave. So this is joint work with Silvio, Lattanzi, Sergei, Vassilvitskii, and Morteza, all at Google. Yes. Can you all hear me? Okay. All right, so what am I going to talk about? So basically, I'm going to talk about low-rank approximation, and the basic problems here are things like PCA and column subset selection. And these are some of the most fundamental problems in data analysis. PCA is often used for dimension reduction. And the goal is to reduce the data from high dimensions to a lower dimension while somehow preserving the signal. And column subset selection is you have a matrix with a huge number of features or columns, and you want to pick a subset of them that in somehow capture, that are somehow representative of the rest of the columns. And these are also very natural problems in numerical linear algebra, and lots of communities have studied these kind of problems. Okay? So let me just formally state PCA anyway, because I will also state a slightly different formulation. So the easiest formulation is the following. You have data in d-dimensional space, and you want to find a k-dimensional subspace such that the sum of the squared distances of the points to the subspace is as small as possible. And an alternate formulation, which is actually what we'll use more for this talk, is the following, where you are given some matrix, and you want to decompose this matrix U that you are given into some m times x, where m is an orthogonal matrix, okay? And x is what I will call the embedding of the vector ui. Okay? So xi is the embedding of the vector ui. So it basically is a set of coefficients that allow you to represent vectors of u in the basis given by m. Okay? So this is one way to define PCA. Okay? And here, of course, there's extensive literature. I just wanted to mention a few things about how you can actually compute it in near linear time in input sparsity. There are also lots of algorithms, including streaming algorithms and so on. So the other problem that will be of interest is column subset selection. So this is, here, instead of finding a subspace, now we want to find some k columns of the original matrix with the property that if you project the other columns onto the space orthogonal to the span of these columns, then you have the mass is as small as possible. Okay? So you want columns that capture as much of the total mass of the L2 mass of the matrix. Okay, so that's column subset selection. Okay, and this kind of a problem is used often in practice for things like feature selection, and there are also lots of efficient bicriteria algorithms that are known for this problem. And it turns out that the problem is also closely related to PCA itself. Okay? So there's a tight connection between column subset selection and PCA that some of these algorithms actually use. All right, so now I would like to talk about online algorithms for these problems. Okay, and what is the online setting? So here you have points or these columns. They show up one by one. Okay? And in general, in online models, points come by, and you need to make decisions as soon as the points arrive. Okay? And that's the main restriction. Okay? And the goal is often to compete with the total error in hindsight, okay, with the optimum error in hindsight. Okay? So that's the general goal in online algorithms. So let me define it for column selection, as it will be a little bit easier. Okay? So here you have some columns that show up. Okay? So these are some d-dimensional columns. And each time a column arrives, you either keep it or you don't, or you just let go of it forever. Okay? And your goal is to keep roughly k columns at the end. Okay? And you would like to compete with the best S that has k columns. And the best is defined in hindsight. Okay? So that's the goal of online column subset selection. And you can think of it as, in some sense, some linear algebra analog of you want to hire some k secretaries kind of a problem, right? So you have this function f of s that's defined by how much mass columns of s capture, and you would like to build this set s in some online way. Okay? So that's the online column selection problem. And what is PCA? PCA is a bit more tricky to define. This is why I defined this notion of embeddings before. Okay? And the way online PCA is defined is you get these vectors in d-dimensional space. Okay? And the moment a vector shows up, you would like to commit to an embedding xi of this vector ui. Okay? And so that's what you've got to do. So once a column arrives, you have to produce a short embedding of this column. Okay? And in the end, you must have the guarantee that there is some orthogonal matrix M such that you can interpret these embeddings as embeddings into that basis. Okay? And now you must have error that hopefully competes well with the best low rank approximation. Okay? With the error of the best low rank approximation. Okay? So this is the online PCA problem. All right. So what is known about these problems? So for online PCA, so paper by Boutsidis and others in 2015, so what they showed is that given any epsilon, you can produce an embedding into something like k by epsilon squared times polylog n dimensions, and you obtain some kind of an additive approximation. Okay, so what you get is an error guarantee like the error that you produced, okay, of this of the best using the best m. Okay, so that is smaller than or equal to the best low rank error plus epsilon times the Frobenius mass of the whole matrix. Okay. And this actually, the online model turns out to be much harder than streaming PCA. So in streaming, you can actually get multiplicative approximations. But so far, the best thing known for online version of PCA was just this additive error bound. Okay. And nothing essentially was known for the online version of column subset selection. Okay, and one of our motivating things was, are there like clean multiplicative approximations to online PCA and column selection? Okay. So what we could show is not quite a multiplicative approximation, but the following result. So what we said, what we can show is there is an efficient online algorithm, okay, that embeds vectors into dimension something like k times polylog of 1 by epsilon instead of 1 by epsilon squared, while achieving the same bound as the Boutsidis et al. Result. Okay, so it's like you have your error is less than or equal to essentially the best rank A error plus epsilon times the Frobenius norm. So there is still this additive term, okay, but you get only like a log, polylog in this dependence on this additive term. Okay. There is also a small 1.1 here, which if you are careful, you would notice. Okay, so that is not very important. You can bring it down as much as you want. Okay. All right. So this has a significantly better dependence on epsilon, like I was saying. And yeah, if you think about it, this is a multiplicative approximation for many purposes, right? So it's like often your ratio of the best error to this will not be too tiny. Right? So. And one of the things is that the algorithm itself is very simple, and it's inspired by online clustering. There's a very beautiful algorithm of Myerson, which I will talk about a little bit, and our algorithm is basically inspired by that. Okay. And for the online version of column subset selection, what we show is a very similar result, except that the dependence on the log is a little bit better. Okay. And you might think that column selection is often harder than PCA, but it turns out that it's basically the analysis that causes this. 10 left, right? Yeah, okay. All right, and yeah, and like I was saying, both of these algorithms are inspired by Myerson's algorithm for online clustering. Okay, so let me just mention this algorithm briefly. So I'm guessing many of you might have seen it, but the problem is as follows. You have points u that arrive one by one, okay? And let's say your goal is k-means clustering. Okay, so you want to minimize the k-means objective. That's the problem. And points arrive one by one. Each time a point shows up, you have to either add it to some set, okay, or set of centers that you are maintaining, or you just lose it forever. Okay? And the problem is very similar. In the end, you want roughly k points in your set, okay? And somehow you want that the objective that the k-means objective that you have using this set S as centers is something that is close to the optimum k-means objective. Okay? So this is the goal in online k-means. And what the algorithm that Myerson gave is very simple. So suppose you know what the value of the optimum is. Okay? And what he said is, let's say you add a point u that you see to the set S with basically probability proportional to the squared distance of u to all the points you've chosen so far divided by this guess for the optimum, okay, times some multiplicative factor which is essentially k. Okay? And you threshold it at 1 so that because these are probabilities. And suppose you just do this for every point that you have. Okay? And the claim is that this actually yields a good competitive algorithm for k-means. And why is this? So actually, the proof is quite simple. I mean, at least at a high level. So this is a caricature proof. And the idea is, let's say you look at some optimal cluster C. Okay, so this is the optimal cluster C. And you just look at the sum of dus square values. Okay, so these are just the square distances to the points that you've chosen so far. Okay. Then the claim is that if this sum over all these points of this quantity, if it's more than something like C by K, then this probability will ensure that you will actually pick one of these points with very high probability. Okay, so you'll pick some point of this cluster with some pretty good probability, and if this sum is less than C by K, then somehow, even if you had K clusters like this, you just have something like their contribution adds up to something less than C. Okay, so I mean, of course, this is not a formal proof because the S keeps changing, and maybe these dus values will change with time. Sometimes they will reduce with time and so on. So this is not a formal proof, but this is the rough idea of the proof. Okay, so it's very simple. Okay, so and the nice thing here, if you think about it, is that somehow the probability is tied to the contribution to the objective, okay? And that's why you're able to get this argument to go through. Okay, and one of the questions we asked is, are there like similar clean algorithms for PCA and CSS type problems? Okay, and let me define the setting for the sake of the talk. Okay, so there are a couple of assumptions we'll make. So firstly, we'll consider only PCA, and we'll always call the input matrix U, and the columns of this will be called UI. And more importantly, what we assume is that you know some target error C. Okay, and that error satisfies this quantity. The important thing is that I'm assuming I know this quantity, okay? And this is what I will assume, and note that this is what we are actually interested in proving is way more than this quantity, okay? All right, so let's start with some C that we know and satisfies this property, all right? And so the rough algorithm will be very similar to Myerson's, okay? So it will maintain some subspace S, and it will add dimensions one by one to this subspace when necessary. Okay, and remember that in the problem you've got to produce an embedding of a vector as you get it, right? So and the embedding will just be the projection onto the current set of current subspace that you have. Okay, so so this is the general framework, and here's if you would like to mimic Myerson's algorithm in this context, then what you would do is, suppose you have this target error C. Okay? Now you can say the probability that I add a point is basically proportional to the projection of the point I got orthogonal to the space I have. Okay? And you normalize it by C, and you multiply by K. Okay? So let's call this probability P sub I. Right, and if you think about this is in some sense something like one pass adaptive sampling, because you get these points, and each time you keep a point with this probability, otherwise you discard it and it goes forever. Okay, and if this works out, then this would actually give a very Myerson-like algorithm for online PCA and column selection. Okay, but unfortunately we don't know how to analyze this particular version, and in fact we think that this is not quite optimal. There's some extra log factors and so on, and but what we propose to do is analyze a slight alternative of this algorithm. Okay? But before we go to that, what I would like to say is that one claim which is at the heart of our argument is that somehow you can't have too many indices I for which this pi is large, okay? Which means that the probability that you add this point is quite large. In fact, yeah, so I would like to show that the number of I for which pi is bigger than or equal to 1 is actually quite small. Okay? And this is done by a very clean argument, so that's why I would like to show it. And basically, what does it mean that a bunch of pi's are large? Right? So it means that for all these vectors ui, you have a large component orthogonal to all the previous guys. Okay? So each ui has a large component orthogonal to all the previous ones. And if you have this kind of a property, you can show this pretty simple geometric lemma. It says that if you have a bunch of vectors such that for every I, the length of the projection is at least some xi by k, okay? And you also know that xi is some upper bound on the best rank k approximation, right? So if you have this property, then R cannot be too big, okay? And the proof of this is very simple. It says that in some sense, this implies that there are lots of orthogonal directions in your UIs. And this forces the rank k error to be strictly larger than xi, which will be a contradiction. Okay? So that's the rough idea of this proof. Okay? So this works as long as these pi's are large. Okay? And it turns out that the issue is if p's are small. Okay? So if the p's are tiny, then this argument cannot be used. And in some sense, this is a problematic case because if p is pretty tiny, then you get these columns with some good probability, you don't choose them, and then they're gone forever. Okay? And it's an online algorithm, so you have no memory of what you've seen. Okay? And so this is what we fix by looking at a variant of the algorithm. And the idea is just you look at these vectors in phases, and in some sense, each phase is just a set of vectors whose p-values add up to 1. Okay? So, and what we do is at the end of each phase, we add some one direction to this set S. Okay? And this one direction will, in some sense, be a sketch of all the vectors in that phase. Okay? So we keep track of a running sketch. So instead of throwing away a point if its p-value is too small, we keep some kind of a sketch of this vector. And and this is how I define the sketch. Okay, so it's some signed random linear combination. Okay, so let me not get too much into the details of this because I'm probably out of time. Okay, so, but the nice thing is that by doing this, it turns out that you can apply this geometric lemma that I was talking about, but to the sketches. Okay, and that's a nice fact. So it shows that the number of phases that you have is small, which in turn implies that the number of columns you are adding to this space S is pretty small. Okay? And one nice thing about our definition of this probability is that as long as the number of phases is small, okay, the total error is automatically bounded because the total error in a phase is less than or equal to something like c by k because these probabilities added up to 1. Okay? So the total error in a phase will be less than or equal to c by k. And that's why the bound on the number of phases also implies a bound on the total error. Okay. All right, so this gives some bound of this kind. So it gives a bound like the total error is smaller than c times some log factor. Okay, but what we wanted is something like c times 1.1, right? So how do you get to this? So it turns out that if you can do this using an additive approximation algorithm as a black box, if you could do like 2 passes over this data. Okay? But this is an online algorithm, we are not allowed to do 2 passes, but it turns out that you can actually simulate both the passes in parallel. Okay? And it needs some technical effort, but you can show that this also ends up, it basically ends up simulating a 2-pass algorithm. And that's it. Okay, so this gives the bounds that I claimed. Okay, so it shows that you get a bound roughly similar to what we had before, where the error is comparable to the best rank k approximation plus some epsilon times the Frobenius norm error. But the dependence of this dimension on epsilon is like polylog 1 by epsilon. Okay, the same is true for column subset selection. And all right, so let me end with like a few open questions. So one thing that I didn't, as I was saying, we don't know if like a vanilla 1-pass adaptive sampling actually gives any bound. Okay? we didn't go too much into it because we thought that this is actually, we had some examples that showed that this gives worse bounds. So it's a simple algorithm, but it gives a little bit worse bounds. Okay. And the other thing is, other question is, can we fully get rid of this additive factor? Like right now, the dependence on this epsilon is small, but it would be nice if there is no additive factor. Okay. And and these kind of problems turn out to be much harder for things like spectral norm approximation and so on. In online algorithms turn out to be really difficult. So that would be something interesting to think about. Okay. All right. Thanks. Thanks for being here until the very end.
Particular situation that you keep in mind when this additive term is not an additive but really a multiplicative term, like it's a canonical situation?
Yeah, so if you assume that this Frobenius norm of the whole thing is some polynomial factor of this thing, like some poly n times the rank k error.
Okay. And that would happen, let's say, if like this U was randomly not randomly generated, I suppose, but like some
yeah, so as long as it's like, as long as U is some rank k matrix plus some error that is not too tiny. Okay, so if it's if that error is like 1 by poly n times the Frobenius norm of the whole thing, then you can get it.
I guess if it's 0, then it's easy to do. If like it was a perfect k subspace, you
right.
could probably.
Right. So that's why I think it may be possible to get rid of all of these things. But yeah.
Any other question? No?
Yeah.
Can we consider this process streaming, or?
Yes. So this is a strictly harder model than streaming. Okay. And so the other thing we know is that for any of these adaptive sampling type algorithms, this log 1 by epsilon is actually necessary. So you can't actually get rid of that. So yeah, I wouldn't. Yeah. Although I have hope, I wouldn't be too sure that this is possible in an online model. Yeah, so streaming, these problems are actually known. You don't even need something like this. You can just get a plain multiplicative approximation. Okay. And because the goal in streaming is just to come up with like the optimal subspace at the end. And so the point is that you can keep track of principal directions, and at some point you can realize that, oh, some of them were not really useful, so you can throw them out and you can do this. But in an online algorithm, if you've built up stuff, you can't lose it. Yeah. So yeah.